Structure of an Atom by Hassan Malik. In this chapter, we will talk about the structure of an atom, which consists of a central nucleus containing protons and neutrons surrounded by electrons and orbitals. Structure of an atom, grade 9/O levels, part 1, chemistry 1. Theories related to atomic structure: Dalton's atomic theory, Thomson's pudding model, Rutherford's nuclear model, Bohr's model of the atom, Sommerfeld's model, Heisenberg's uncertainty principle, Grounder's wave equation, Dirac's model, Planck's quantum hypothesis, modern quantum mechanical model. Experiments related to atomic structure: Rutherford's gold foil experiment, Milkins oil drop experiment, Thomson's cathode ray tube experiment, Ravenson-Germer experiment, Stern-Gerlach experiment, photoelectric effect experiment, double slit experiment, compound effect experiment, Bernard-Head experiment, Franz-Castellan effect experiment, discharge tube experiment. History of atomic theory: ancient philosophy and early concept. Democritus concept proposed that matter is composed of small indivisible particles called atoms, meaning uncuttable or indivisible. Limitations: lacked experimental evidence and was purely philosophical. Aristotle concept rejected by Democritus' atomic theory, believed in the four elements: earth, water, air, and fire. Influence dominated scientific thought for nearly 2,000 years. History of atomic theory: Islamic golden age of science. Al-Kindi, known as a philosopher of the Arabs, significantly advanced various scientific disciplines, particularly chemistry. His writings synthesized Greek philosophy with Islamic thought, focusing extensively on the nature of matter and the concept of atoms. Al-Kindi's contributions laid foundational insights into the properties and composition of substances, which later informed significant developments in the field of chemistry. Al-Razi, a prominent alchemist and physicist, explored the transformation of substances and the properties of matter. Although he didn't directly theorize about atoms in the modern sense, his meticulous experiment methods and classification of substances contributed to the later understanding of atomic theory. He wrote about the differentiation of matter and the chemical processes that change substances, laying groundwork for future atomic concepts. Jabir ibn Hayyan, foundation of alchemy. Often regarded as a father of chemistry, Jabir developed numerous chemical processes and theories about the composition and transformation of substances. He wrote extensively on the nature of elements and their interactions, hinting at the existence of fundamental particles that constitute matter. His practical experiments and theoretical insights laid the groundwork for future scientific exploration, including the concept of atoms. Al-Farabi, metaphysics and matter. Al-Farabi explored metaphysical concepts and the nature of the physical world, discussing the existence of indivisible particles. His philosophical treatises contributed to the understanding of matter's composition, incorporating the ideas of earlier Greek philosophers like Democritus and Aristotle. Ibn Sina discussed the nature of matter and elements in his extensive philosophical and scientific writings, particularly in the Book of Healing and the Canon of Medicine. He considered the composition of substances and elements, proposing that all matter is composed of basic elements, which aligns with the idea of atomic composition in a broad sense. His ideas influenced later Islamic and European scholars, uh, bridging the gap between ancient and modern scientific thought. Revival of atomic theory. Scientists Robert Boyle, Isaac Newton. Contribution. They supported the idea of atoms by exploring their role in chemical reaction and investigating the properties of gases. Their work laid crucial foundations for the development of modern chemistry and physics, making a significant shift toward understanding matter at its fundamental atomic level. Dalton's atomic theory, modern era. John Dalton was an English chemist, physicist, and meteorologist. He is best known for his pioneering work in the development of modern atomic theory and his research in color blindness. Postulates all matter is composed of extremely small particles called atoms. All atoms of a given element that are identical in mass and properties. Compounds are formed by the combination of two or more different kinds of atoms. A chemical reaction is a rearrangement of atoms. Experimental evidence, law of conservation of mass, law of definite proportions, law of multiple proportions. Limitations. Dalton claimed that atoms are indivisible, but later discoveries showed that atoms can be divided in subatomic particles. The discovery of isotopes contradicted this postulate. Conclusion. John Dalton's atomic theory was a pioneering step in chemistry, providing a foundational framework for understanding the nature of matter, chemical reactions, and compound formation. Despite its limitations, such as inability to account for subatomic particles and isotopes, the theory introduced key concepts like the conservation of mass and definite proportions. These ideas paved the way for future discoveries and advancements in atomic structure and quantum mechanics, cementing Dalton's role in development of modern chemistry. Thomson's plum pudding model. J.J. Thomson, full name Sir Joseph John Thomson, was a British physicist who was best known for his discovery of the electron and his development of the plum pudding model of the atom. Thomson's postulates atom as a uniform sphere, electrons and protons embedded, electrostatic balance. Experimental evidence, discovery of the electron, uniform distribution of charge. Limitations, lack of a central nucleus, electromagnetic instability, no explanation for atomic spectra. Thomson's plum pudding model was an early atomic model proposing that electrons are embedded in a positively charged sphere while groundbreaking. It was later disproven by Rutherford's experiments, which revealed a central nucleus despite its eventual replacement. It was a pivotal step in advancing atomic theory. Rutherford's nuclear model. Ernest Rutherford, often referred to as the father of nuclear physics, was a New Zealand-born British physicist. He is best known for his discovery of the atomic nucleus in 1911, discovery of proton in 1917, and for his model of the atom, which described a central positive nucleus surrounded by electrons. Postulates positively charged central nucleus, electrons in orbit, empty space. Experimental evidence alpha particle scattering gold foil experiment. Limitations stability of electron orbits, quantization of energy levels, quantum mechanics. Conclusion. Rutherford's nuclear model established that atoms consist of a dense, positively charged nucleus surrounded by orbiting electrons, with most of the atom's volume being empty space. It explained the scattering of alpha particles through gold foil and marked a departure from the early plum pudding model. However, it could not account for the stability of electron orbits or the discrete spectral lines observed in atomic spectra. Bohr's model of the atom. Niels Bohr was a Danish physicist who made foundational contributions to understanding atomic structure and quantum mechanics. He is best known for developing the Bohr model of the atom, where electrons orbit the nucleus in defined energy levels. This model introduced the idea that electrons could jump between energy levels, emitting or absorbing specific amounts of energy. He received the Nobel Prize in Physics in 1992 for his work on the structure of atoms. Postulates quantized orbits. Electrons orbit the nucleus in specific fixed energy levels without emitting radiation. Energy transitions. Electrons can jump between these levels by absorbing or emitting a photon with energy equal to the difference between the levels. Angular momentum quantization. The angular momentum of an electron in orbit is quantized and given by L equals nh, where n is an integer, the principal quantum number, and h is the reduced Planck's constant. Experimental evidence. Hydrogen spectral lines. Bohr's model successfully explained the discrete spectral lines of hydrogen, particularly the Bohm series. Rydberg formula. The model provided a theoretical basis for the Rydberg formula, which describes the wavelengths of spectral lines. Limitations. Applicability. The model works well only for hydrogen-like atoms and fails for multi-electron atoms. Electron behavior. Bohr's model could not explain why electrons do not radiate energy while orbiting, or how the electrons' orbits are stable. Quantum mechanics. The model was superseded by a more accurate and comprehensive quantum mechanical model, which accounts for electron wave functions and probability distributions. Zeeman effect. Conclusion. Bohr's atomic model was a groundbreaking step in the understanding of atomic structure, introducing the concept of quantized energy levels and providing a framework to explain the spectral lines of hydrogen. While it successfully addressed certain limitations of classical physics, it also had its own limitations, particularly in its applications to multi-electron atoms and its explaining more complex phenomena like the Zeeman effect. Despite these shortcomings, Bohr's model laid the foundation for the development of modern quantum mechanics. R. Sommerfeld's model. Arnold Sommerfeld was a German theoretical physicist who made significant contributions to the field of quantum theory and atomic physics. He was well known for his work on the fine structure constant and for developing the Sommerfeld quantization rules, which extended Bohr's model of the atom to include elliptical orbits, leading to a more accurate prediction of spectral lines. Postulates. Elliptical orbits. Quantization of angular movement. Quantization for overall shape. Relativistic corrections. Fine structure constant. Magnetic quantum number. Experimental evidence. Fine structure of spectral lines. Zeeman effect. Anomalous Zeeman effect. Fine structure constant. Rydberg constant. Refinement. Limitations. Inability to explain the anomalous Zeeman effect, lack of a complete explanation for multi-electron atoms, relativistic effects only partially addressed, semi-classical nature of the model, inability to predict certain spectral lines, failure to explain electron spin, complexity in mathematical inconsistency. Conclusion. Arnold Sommerfeld's extension to the Bohr model marked an important step in atomic theory, introducing elliptical orbits and relativistic effects to better explain the fine structure of spectral lines. However, his model had limitations, particularly in addressing multi-electron atoms and the anomalous Zeeman effect. These shortcomings highlighted the need for a more comprehensive framework, which was eventually provided by quantum mechanics. Despite being surpassed, Sommerfeld's work was crucial in the transition. Heisenberg's uncertainty principle. Werner Heisenberg was a German theoretical physicist who was best known for formulating the uncertainty principle, a fundamental concept in quantum mechanics. This principle states that that it's impossible to simultaneously know the exact position and momentum of a particle. For his contributions to quantum theory, Heisenberg was awarded the Nobel Prize in Physics in 1932. Postulates uncertainty in position and momentum, limits of measurement, implications for quantum mechanics. Experimental evidence, electron diffraction, Heisenberg's microscopic thought experiment, gamma ray microscope experiment, atomic and subatomic particle measurements. Limitations. Microscope scale, interpolation challenges, technological limits, alternative formulations, quantum entanglement. Conclusion. Heisenberg's uncertainty principle is a fundamental concept in quantum mechanics, revealing that certain pairs of properties like position and momentum cannot be precisely simultaneously known simultaneously. This principle highlights the probabilistic nature of quantum systems and marks a clear departure from classical physics. While its effects are minimal on a microscopic scale, the uncertainty principle is crucial for the understanding the behavior of particles at the quantum levels and remains a key idea in modern physics. Schrodinger's wave equation. Erwin Schrödinger was an Austrian physicist renowned for his foundational work in quantum mechanics. He is best known for developing Schrödinger equation, which describes how quantum systems evolve over time. Postulates wave function representation, linear superposition, time evolution, Hamiltonian operator, boundary conditions. Experimental evidence, hydrogen atom spectra, electron diffraction, quantum tunneling, double slit experiment, atomic orbitals. Conclusion. Schrödinger's wave equation is a foundational element of quantum mechanics, providing a powerful framework for understanding and predicting the behavior of quantum systems. Experimental evidence, including the accurate prediction of hydrogen atomic atom spectra, electron diffraction, quantum tunneling, atomic orbitals, confirms the validity of Schrödinger's equation. This equation describes particles as wave functions, offering insights into phenomena that classical mechanics cannot explain. Despite its success, Schrödinger's equation has limitations. Dirac's model. Paul Dirac was a British theoretical physicist and one of the pioneers of quantum mechanics and quantum electrodynamics. He is best known for his formulation of the Dirac equation, which describes the behavior of fermions and predicted the existence of antimatter. Postulates: Dirac equation, antimatter, quantum electrodynamics, Dirac-C magnetic monopoles, Fermi-Dirac statistics. Experimental evidence: discovery of the positron, fine structure of hydrogen, magnetic momentum of the electron, anomalous magnetic moment, and quantum electrodynamics behavior of fermions. Limitations: Dirac-C concept, incompleteness of quantum electrodynamics. Conclusion: Paul Dirac's work revolutionized physics with the Dirac equation, which accurately described impermanence and predicted antimatter. His contributions laid the foundation for quantum electrodynamics and ferromanagnetic statistics. However, some aspects like the Dirac seed concept and magnetic monopoles had limitations and were later refined or superseded by more advanced theories. Despite these limitations, Dirac's theory remained foundational, with his predictions closely aligning with experimental results. Planck's quantum hypothesis. Max Planck was a German physicist known as the father of quantum theory. His work laid the foundation for modern quantum mechanics and significantly altered our understanding of atomic and subatomic processes. Postulators, quantization of energy, Planck's constant, black body radiation, discrete energy levels, statistical mechanics. Experimental evidence, black body radiation, photoelectric effect, compound scattering, atomic spectra, black body cavities. Conclusion. Max Planck's quantum theory revolutionized our understanding of atomic and subatomic processes by introducing the concept of quantized energy. His postulates, including the quantization of energy and the role of Planck's constant, successfully explained black body radiation, led to the development of quantum mechanics experimental evidence, such as the validation of Planck's law in black body radiation. Einstein's explanation of the photoelectric effect and compound scattering confirms the accuracy of Planck's theories. Modern quantum mechanical models. The modern quantum mechanical model of the atom, primarily based on quantum mechanics and quantum field theory, represents a significant advancement from earlier models like Bohr's and Sommerfeld's. Postulates: quantum mechanics, wave-particle duality, quantum field theory, standard model of particle physics, string theory, loop quantum gravity, quantum computing. Limitations: interpretal challenges, complexity and computational limitations, incompatibility with general relativity, lack of understanding of quantum gravity, non-locality and entanglement, interpretational paradoxes. Experimental evidence, double slit experiment, photoelectric effect, Stern-Gerlach experiment, Bell's theorem in quantum entanglement, quantum superposition and Schrodinger's cat experiments, quantum tunneling, quantum computing, and coherence experiments, quantum Zeno effect. Conclusion: quantum mechanics is a highly successful theory that explains the behavior of particles at the atomic and subatomic levels, confirmed by key experiments like the double-slit experiment and the photoelectric effect. However, it has limitations such as the inferential challenges like the measurement problem, difficulties in reconciling with general relativity, and the complexity of modeling large quantum systems. Despite these issues, quantum mechanics remains a fundamental and powerful tool in modern physics, driving technological people. Rutherford's Goldfoil experiment. Rutherford's Goldfoil experiment showed that alpha particles, when directed at a thin gold foil, mostly passed through, but some of them were deflected at large angles. This led to the discovery that atoms have a small, dense, positively charged nucleus at their center, surrounded by mostly empty spaces. Finding overturned the plum pudding model and established the nuclear model of the atom. Millikan's oil drop experiment. Millikan's drop experiment in 1909 measured the charge of the electron by observing oil droplets suspended between charged plates. He determined that the droplets carried charges that were multiples of a fundamental value. Identifying this as a change of a single electron confirms the quantization of electric charge. Thomson's cathode ray tube experiment. Thomson's cathode ray tube experiment discovered that electrons by showing that cathode ray tube were deflected by electric and magnetic fields. This demonstrated that atoms contain negatively charged particles, leading to the plum-pudding model of the atom. Davidson-Germer experiment. The Davidson-Germer experiment demonstrated the wave nature of electrons by showing they could produce an interference pattern when scattered off a crystal surface. This experiment confirmed the hypothesis of matter waves, providing evidence for wave-particle duality. Discharge tube experiment. The discharge tube experiment involves passing electric current through gas at low pressure contained in a glass tube. Stern-Gerlach experiment. The Stern-Gerlach experiment demonstrated the quantization of angular momentum, showing that silver atoms passing through a non-uniform magnetic field split into two distinct paths. This experiment proved direct evidence of quantum spin and the quantized nature of particle properties. Photoelectric effect experiment. Einstein's photoelectric experiment showed that light ejects electrons from a metal surface only when its frequency exceeds a certain threshold. Regardless of intensity, this demonstrated that light insists quantized spikes of energy called photons, confirming the quantum nature of light. Double slit experiment. The double slit experiments, first conducted by Thomas Young in 1801, revealed that light and particles such as electrons create an interference pattern and pass through two slits. This pattern changed the stopic waves, indicates the particle exhibit wave-particle duality, behaving it's both waves and particles depending on observation. Compound effect experiment. The compound effect experiment demonstrated that X-ray photons scattered off an electron, those energy resulting in an increase in wavelength. This confirmed that light behaves as particles and provide evidence for the quantization of energy, supporting the particle theory of light and validating the concept of photon momentum. Frank Hertz experiment. The Frank Hertz experiment demonstrated that electrons collide with atoms in a gas and transfer energy in discrete amounts, causing the gas to emit light at specific wavelengths. This provided evidence for quantized energy levels in atoms, supporting the Bohr model of the atom. Franz-Kegels effect experiment. The Franz-Kegels effect experiment observed that an electric field applied to a semiconductor changes the optical absorption properties, causing shifts in absorption spectra. This effect provided light into the behavior of electrons in semiconductors under strong electric fields and in understanding electronic band structures. Protons, positively charged particles located in the nucleus of an atom. They define the atomic number and element identity. Neutrons. Neutral particles found in the nucleus contributing to the atomic mass and stabilizing nucleus. Electrons, negatively charged particles orbiting the nucleus in electron shells or energy levels. They are involved in chemical bonding and reactions. Quarks, fundamental particles that combine to form protons and neutrons. There are 6 types of quarks: up, down, charm, strange, top, and bottom. Neutrinos, extremely light neutral particles that interact via the weak force, playing a role in processes like radioactive decay. Leptons. Leptons are fundamental particles in the Standard Model of particle physics that do not participate in the strong nuclear force. Bosons. Bosons are a class of fundamental particles that mediate the fundamental forces in the Standard Model particle physics. Unlike fermions, which obey the Pauli exclusion principle, bosons can occupy the same quantum state. Gluons, particles that mediate the strong force binding quarks together within protons and neutrons. Photons. Photons are massless particles of light that mediate the electromagnetic force. They travel at the speed of light and have energy related to their frequency. Hadrons. Hadrons are composite particles made of quarks bound together by the strong force. Such as baryons, such as protons and neutrons, which are made of 3 quarks. Mesons, such as pions and kaons, which are made of 1 quark and 1 antiquark. Antiparticles. Antiparticles are contraparticle particles with the same mass but opposite charge and quantum numbers. For each particle, there is a corresponding antiparticle with opposite properties. Fundamental forces. The fundamental forces are the 4 basic interactions that govern the behavior of matter: gravity, electromagnetism, strong force, and weak force. Gravitational force attracts objects with mass. It is the weakest force but has an infinite range. It is described by general relativity. Electromagnetic force acts between charged particles. It is much stronger than gravity and has an infinite range. It governs electric and magnetic interaction and is described by quantum electrodynamics. Weak nuclear force responsible for radioactive decay and other processes involving particle reactions. It is short range and is described by the electroweak theory. Strong nuclear force binds quarks together within protons and neutrons and holds atomic nuclei together. It is the strongest force and acts over very short distances, described by quantum chromodynamics, or QCD. God's equation of physics. God's equation is a term often used to refer to the idea of a unified theory that explains all fundamental forces and particles in a single framework. The end. Thank you for watching.